Okay, so let's quickly talk about gravity and how to do gravity problems. So for gravity, what we know is Newton's law that the force between two objects is going to, of course, be equal and opposite action-reaction pairs. The gravitational force between two masses is a constant g, which is a very small number, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, times m1 times m2, so it's proportional to the masses, and it's inversely proportional to the distance between them squared, and it's an attractive force just along the line between the two objects. Make sure you don't get the uppercase g, the universal gravitational constant, mixed up with lowercase g of 9.8 meters per second squared when you do these problems. So what is little g? So near the surface of the Earth, we know from earlier chapters that the weight, the gravitational force, is the mass of the object times little g. And so Newton's gravitational law tells us that should also be equal to big G times the mass times what it's attracted to, which is the mass of the Earth. And the distance should be the radius of the Earth, because the object is right at the surface of the Earth, the radius of the Earth squared. And so if that's correct, then little g should be equal to big G times the mass of the Earth divided by the radius of the Earth squared. And in fact, if you put the numbers in, you do get that little g is equal to 9.8 meters per second squared. Of course, little g varies over the Earth's surface due to altitude, local geology, the shape of the Earth, which is not quite spherical, but on average it's 9.8 meters per second squared. So of course, on different planets, because the different planets have different masses and different radii, the attraction of an object to that planet, the little g, will be different. So that's why the astronauts on the moon, if you look at videos of them, are bouncing along, because the gravitation of the little g is a lot smaller. It's about 1.7 meters per second squared on the moon, so they feel lighter. Okay, satellites orbit around a planet, and when they orbit around a planet, so let's say, for example, a satellite orbiting the Earth, what has to happen is that the speed has to be high enough that the satellite does not return to the Earth, but not high enough that it goes flying off into space. So if you want to go in a circular orbit, the minimum speed for a satellite is 27,000 kilometers per hour. If you make it go faster and faster, it goes more and more from circular to being an oval shape, an ellipse. And if you go to 40,000 kilometers per hour, the speed is fast enough that the gravitational attraction of the Earth is not sufficient to keep it moving in a circle, and then it will escape. So if they want to send something out to the edges of the solar system, they have to give it at least a 40,000 kilometer per hour initial speed. So when something is orbiting in a circular loop around the planet, the centripetal force is provided by the gravitational force. So remember, centripetal force is mv squared over r, and gravitational force is gmm over r squared. And so the satellite is kept in orbit just by its speed. So if we had the satellite stop moving, it would fall down to the Earth. So what's happening as it goes around the planet is that it's continually falling to the Earth, but the speed keeps pushing it further out. So as it falls, it keeps getting pushed further out back onto the circular orbit. So it's continually falling. And that's why people on the space station that's in orbit around the Earth, it's like they're in free fall. It's not that they don't have any gravitational attraction to the Earth. It's just that they keep moving away from the Earth as they fall, so that they stay a constant distance away at all times. Satellite problems are great problems for me to give you on the test for Module 5, because it's a way for me to test you on both circular motion and gravitational force at the same time. So take that as a strong hint that you need to be able to do these kind of problems. So let's do one sample problem. So during the moon missions, the command module, which stayed in orbit around the moon, was in orbit at an altitude of 100 kilometers. And we want to know how fast must it have been going to stay in orbit at that height, and how long did it take to orbit the moon once. And to know that, to be able to solve this problem, we need to know the mass of the moon and the radius of the moon. So on a test, I would give you the mass and the radius of any planet that you needed to know. So the mass of the moon is very big. It's 7.36 times 10 to the 22 kilograms. And the radius is 1.74 times 10 to the 6 meters. So how are we going to do this problem? Well, first thing is to gather the numbers. The only number I have is 100 kilometers, which is, if I draw that picture there, it's the distance above the surface of the moon that the satellite is orbiting in. And of course, that picture isn't drawn to scale. Okay, so the equations that I have is the period. So that's what I'm trying to find when it says how long did it take to orbit the moon once, is 2 pi r over v. The centripetal force is mv squared over r. And the gravitational force is g times the mass of the moon times the mass of the satellite, which is the command module in this case, the cm, divided by r squared. So in order to solve this, we have to know what r is. On r in this case is going to be the distance from the satellite, the command module, to the center of the moon. So that distance, total distance there, is going to be r. So how do we get r? Well, r is going to be the radius of the moon plus the altitude above the moon. So it's going to be rm, which is 1.74 times 10 to the 6 meters, plus 100 kilometers. 100 kilometers is 10 to the 5 meters. I got to put the same units. So the radius is 1.84 times 10 to the 6 meters. Okay, so I want to know what's v and what's t. So if I look, I know my r now. I know the mass of the moon. G, big G is a constant. I don't know the mass of the command module. I don't know v, and I don't know t. I'm trying to find v and t. So getting back to my problem, how do I solve it? Well, the one thing I know is that if it's moving around the planet, there must be a force, mv squared over r, towards the center, and that has to be provided by gravity. So I can set those two equations for the forces equal to each other. So mv squared over r equals g m over r squared, where we have a mass of the command module on both sides. So the mass of the command module, that's just going to cancel out. So I don't actually need to know it. So it doesn't matter how heavy the thing is that's in orbit, it's going to cancel out. So now I also have the radius on both sides, so I can cancel out one of the radii. So now my equation is just v squared is equal to g times the mass of the moon divided by the radius of the orbit. And I know all those things, so I can just plug them in. So v squared is equal to g times the mass of the moon over r. So big G, 6.67 times 10 to the minus 11. Mass of the moon, 7.36 times 10 to the 22 kilograms. And the radius of the orbit is 1.84 times 10 to the 6 meters. If I put that all in, I get that v squared is about 2.7 times 10 to the 6 meters squared per second squared, because it's the speed squared. So to get the speed, I have to take the square root. And so v is 1633.8 meters per second, or about 1600 meters per second. So that's pretty fast. All right, what else did it ask for? Well, it asked for the period. So now I know my r, I know my v, so I can just now plug and chug to get my period. So my period, 2 pi r over v, plug in my v that I found in the first part. So 2 pi, the r is 1.84 times 10 to the 6. My v is 1633.8 meters per second. And so I get a period of 7,076 seconds. And that's about 2 hours. So it takes about 2 hours to go around one time. So you should be able to do a quick calculation. The space station takes about 90 minutes to get around the surface of the Earth. So you should be able to calculate, knowing the mass of the Earth, how far above the surface of the Earth is the space station. So make sure that you can do satellite problems like this Remember, the only thing to remember is that when something is in orbit, the two forces are equal to each other. So you set gmm over r squared equal to mv squared over r, and then rearrange to solve for whatever you're asked for. You might be asked for r, you might be asked for v. Okay, so the problem I want you to do today is a simple problem where you've got two balls that have the same mass, and we say that when they're 25 centimeters apart, they experience a gravitational force of 8.8 times 10 to the minus 6 newtons. And so based on that, you won't need to calculate m. Okay, so it's a very simple calculation that you should be able to do quite quickly.